All right, so today we're going to continue our discussion on the convergence in law. So last time, as a recap, we give you the Hessian theorem. So this is the foundation of convergence in law because it's very general. So what this is about is that it gives us the connection or equivalence between convergence in law and convergence of expectation. But the expectation is for some very general function g. So essentially, what it establishes is that the random vector sequence xn converges in law to x. This is equivalent to any of the three things. So the first one, maybe I'll just write it out. In the form, it's expectation of gxn converges to expectation of gx. Because here, expectation is fixed and fixed. So that's why we don't need to say what the mode of the convergence is, because it's just convergence in the real number, in the sense of real number, real vectors. But here, Hessian gives us three conditions of G, and they're going from more restrictive to more general. But any of them is equivalent to the left-hand side, and they are equivalent themselves. So basically, so let me put this as A, statement A. And for here, we have statement B, C, and D. So what this is about, B is about that G is bounded. I just use this, G is bounded, and it actually vanishes outside a compact set. So basically, sorry, maybe I should say G continuous and vanishes outside the compact set, right? So these two things will ensure that G is bounded. So I don't need to say G is bounded. And the second is that G is continuous and bounded. So B is more restrictive, and when B holds, then C must hold. But C contains more functions than B does. Okay, D is the most general. So for D, we just need G bounded and measurable. But here we add an additional condition, that is for the discontinuity points of G, it's not affecting the probability about X. So basically, X is in the continuity set of G with probability 1. So that's the condition for D. And what's amazing here is that although it's natural for us to go from B to C and from C to D, sorry, I should write this, from B to C and from C to D, but because we have a loop, that is D can go to A and A can go to B. So that's why we can have this double directions. So this is something quite amazing. So essentially what it gave us is that A, B, C, and D, each pair is equivalent. So that's why in our homework, right? If you think about the homework problems, you can see which condition, which statement is easier to apply. You can just use it. For example, if you want to show, okay, I have convergence of some G, function G, you can just find the either B or C or D, but just the easiest one to satisfy, okay, that function G satisfy the condition. So given the convergence in law, I can have the convergence in expectation. That's it. You don't really have to prove the statement D. Okay, that's the foundation. And in this class, just for simplicity, I only introduced the one-dimensional case. That is when x, n, and x are one-dimensional random variables. But in the notes, we use the notation of random vectors. So please check that for the d-dimensional case. Okay, now with Hessian, we are now able to prove this foundation. That's Levy's continuity theorem. So you can think about Levy's continuity theorem as a simplification of the right-hand side. You know, even though mathematically the right-hand side is very right, but it's not very intuitive because it's not very easy to think about when we want something to hold for all functions, right? This is for all g, and all g. So it's for any g that satisfies this. So that's not very intuitive to think about. So in Levy's continuity theorem, we just wrap up the right-hand side by what we call characteristic functions. So here we say xn converges in log to x is equivalent to the characteristic function of xm is convergent to the characteristic function of x. That's it. And one thing we need to note is that the characteristic function here itself is bounded and continuous by definition. So I'll just here.
Professor?
Yes.
I'm curious, does it have to converge to phi of x sub n of t for all t or just for some t? Or
for all t, it's all t point-wise convergence. Yeah. So here we don't have, it just depends on the definition of it just depends on the values or the domain of xm. So basically t will be in the same domain as the xm and x. So for example, here, if they are all rd, then t would be rd. If they are all r, then t would be r. Because basically, we just need in the definition of the characteristic function, maybe I'll just write this again as a reminder. So this is defined as expectation of exponential to the power of imaginary unit times t transpose x n. Okay, so basically we need to do the inner product between t and xn. Yeah. And also, I want to say this is bounded and continuous for t. This is a function of t. It's not a function of xn because, you know, when we take expectation, it's about xn. So then xn will go away. And what's left is only about t. All right. So last time we said, okay, to prove this theorem, this direction is straightforward. We just use Hessian. We will just use Hessian to go from A to C, and we're done. And for the other direction, it's not so straightforward, right? Because we still want to use Hessian, but the case is that we're going to go from the special function, this characteristic function, to general function g. And how can we achieve that? That's the difficult thing. And also to go to a general function g, we want to pick, should we go to B or go to C or go to D? And clearly it's easier to prove B because B is having a smaller class of functions, right? D is the most difficult to prove. So that's why we will go to B. So the question is, can we go from the convergence this to B and then to A? So here's the question. How can we go from the convergence of the characteristic function to the convergence of any function g that's continuous and vanishes outside the compact set? That's the question, okay? And we want to actually construct something to make the connection between such g and the characteristic function here. So here, I'm going to briefly talk about the proof because I think it's very, very interesting. So you can see that how things are connected. But the hint is that in order to do this, we actually need to make use of Gaussian random variable as a surrogate or intermediate step. So it's Gaussian is something very easy to use, and Gaussian has a very nice characteristic function, and that's what we'll see. All right, so let's just start this proof to go from this to B. So we just let G be continuous and vanishes outside a compact set. Okay, so basically what we say is that the G is actually bounded. So this will actually give us two things. One is G is bounded. And basically we can write, okay, we can just write the value of G, absolute value of G, I'll just use X to denote the argument, is actually bounded by some upper bound B and for any X. Okay, that's what we mean by bounded. It's just a natural result of a continuous function defined on a compact set. And second, we said this last time. So if it's a continuous function, and if it's only defined in a compact set, it's uniformly continuous. G is uniformly continuous. What does this mean? This means that given any neighborhood size in the value, in the value of G, given any epsilon greater than 0, we can find a neighborhood in the domain of G, neighborhood size in the domain of G, that has nothing to do with this epsilon. Okay, we have this such that whenever we have X and Y with distance less than delta, then we have Gx and Gy differ by at most epsilon. This is the definition of uniform convergence, uniform continuous. And the difference between this and pointwise continuous is that for pointwise continuous, this delta would depend on the X, where the function value is. So for different X, the delta may be bigger, may be smaller. And we may not find a uniform upper bound on delta, so it can blow up. But for uniform continuous, we have this. So the nice thing about the uniform continuity is that given the epsilon, you can divide the compact set where G has non-zero values into small windows. And the delta will be the window size. And then you can make sure that in each window, the difference between values of G of the value of G on that window will differ at most by epsilon. So you can basically control the approximation error for each window. Okay, so given this, we have these nice properties of G, right? And then we want to show B. That is, expectation of Gxn converges to expectation of G of X. This is something we want to show. But how can we make use of the characteristic function? So here is the trick. So the key part is that we introduce a very small Gaussian random variable that takes value close to 0. Okay, so introduce, we call this Y sigma, that follows normal distribution. Okay, again, I'll just make it simpler for you. So I'll just say D equals 1. So everything is a scalar, not a vector. So here, I just make this Y delta follow one-dimensional Gaussian with variance sigma squared. Okay, so you see this sigma is something I can control. When I make sigma small, y sigma will be close to 0. Okay, and then what I want to show is this. So basically, I want to bound expectation gxn minus expectation gx. Okay, I want this thing to go to 0 as n go to infinity, because this is a way to prove the convergence. But here I'm going to give an upper bound. I will bound it by 3 terms. This is a very common technique. So previously in Hessian, we didn't give you the detailed proof last time. So you didn't see this technique, but it was in the notes. So basically we want to give it an upper bound, and we will actually bound it by 3 terms, and then we will show each term will go to 0. And here it is. So the first term is expectation of gxn minus expectation of gxn plus y delta. That's the first term. And the second term is expectation gxn plus y delta minus expectation gx plus y delta. This is the second term. And the third term is expectation g of x minus expectation g of x plus y delta, y sigma, sorry. Yeah. You see, basically if you remove the absolute value, you will see we will have terms canceling each other. Basically, I need to swap these 2 terms. Expectation of gx plus y sigma minus expectation of gx. Then after cancellation, the left-hand side and the right-hand side will be equal without absolute values. But by adding absolute values, I'm basically having this upper bound. So yeah, that's just a very simple property of adding absolute values. And what I want to show is that because I can make the sigma very, very small, then the first term is very small, and the last term is very small, because I'm basically adding y sigma to xn and to x. Then I'm left to show the second term going to 0. And for this one, I can make use of the characteristic function because y sigma is Gaussian. So that's the whole idea. So I want to show this one. This is small, and this is small. And I want to, so my key is about the second term. So let me first give you a very brief idea why this one and this one, the first and third terms are very small. That is guaranteed by the boundedness and uniform continuity. So these 2 things will actually give me why it's very small. Okay, so let's look at the first term. Maybe I'll call this 1, 2, 3. So for the first term, you see, what I can do is to use another trick we have used before. So this one. Okay, so a first trick we can use is that we can get an upper bound by moving the absolute value inside expectation. So this is less or equal than expectation of the absolute difference of gxn and this. Okay, and then with this, I can actually divide this into 2 parts. So first, I know when y sigma is small, I'm good. Because when y sigma is very, very small, then yn plus y sigma is in a small neighborhood of xn. And then by the uniform continuity, I would have their g values differ by epsilon. That's what I will have here. And for y sigma big, right, we know a Gaussian variable is not having a compact support. It's actually having the whole real line as its support. But we know Gaussian is very concentrated around its mean. So the probability for Y sigma being large is very small. So most likely Y sigma will be close to 0. So I'm going to use those two parts. So basically, what I will do is that I will write the right-hand side as two parts. So the first one is this. Let me see. Yeah, sorry. Absolute value gxm minus gxm plus Y sigma. Okay, times the indicator that my Y sigma is very small. That's my first part. And then second part is absolute value indicator Y sigma. Okay, I have these two parts. And that's another trick we used before, right? Introduce some indicator function to divide expectation into two parts. Okay, for the first part, you see what we can say. The first part is regarding when Y sigma is in the small delta neighborhood of 0. So basically here, these two terms only differ by delta. Then by uniform convergence, sorry, I have said uniform continuity, the G to G terms differ by epsilon. So, and here is the absolute, yeah, this is the absolute value. So I just basically less than epsilon. So the first term is less than epsilon, and that's it. So this is what I've bound for the first term. And for the second term, you see, I can use the boundedness to get this part out. So this second term is actually less than what? It's less than expectation of gxn and expectation of gxn plus Y sigma. So basically, I forgot to say absolute value, expectation of the absolute value of each. So I can upper bound it by 2 times b. So b is the upper bound of the absolute value of g times the probability, you see, of Y sigma greater or equal than delta. Because once I get this term out, expectation of indicator becomes probability. Okay, then you see, I can say this is small because I can find sigma. This is something I can define, right? I can find sigma small such that the probability of Y sigma greater or equal than delta is less or equal than epsilon divided by 2b. This is something I can control myself because sigma is arbitrary. Then you see, this term, if I move it down, will be less or equal than epsilon plus epsilon. Okay, 2 epsilon. And that's what I did, how I can bound the first term. So essentially, the key idea is that I can set up sigma to be sufficiently small so that the first term can be upper bounded by 2 epsilon. That's what I did for the first term. So nothing special, just to use the uniform continuity of G and the boundedness of G. Okay. That's why I said the condition B is easier to prove. I mean, statement B in Heidelberg is easier because the G is most restrictive. And similarly, you see, by the same argument, I can bound term 3 by exactly the same argument. So I can bound the term 3 to under 2 epsilon by same argument. Then I'm left with term 2. And term 2 is actually this expectation of gxn plus y sigma minus expectation g of x plus y sigma. And here is why the characteristic function is so important. Okay, we're going to need to use the definition of expectation and the Gaussian density function to write out each term. Okay, so let's say expectation gxm plus y sigma, is defined by what? We just use the definition of characteristic function. We need a double integration because here we have two random variables, xn and y sigma. We have two random variables. The expectation is taken for both. So it's double exponential, you see. We basically need to do gx plus y. And then the density of each, right? What's the density of y sigma? We know it. It's Gaussian. It's actually this. This is the density of y and dy. Okay, and how about the density of xn? Here, we don't know it, right? Because xn can be anything. We didn't specify distribution. So we just write this dfxn. I put it here. It's a little different from the notes. In the notes, I wrote fn, but here I think it's better clarity. I want to say, okay, this is the CDF of random variable xn at value x. And d means that it's differentiation. So I'm just using this general notation. This is the definition of expectation. And then we will see what we can do. So here, first thing we will do is that we will do a change of variable. Basically, what we will change is that we will change the variable from xy to xu. So basically, we will do set this variable instead of g as u, define u as x plus y. So you see, I still have two variables, x and u, and they are one-to-one mapping to x and y. So with this, you see, this integration can be written as what? So I'll just have u and x, and then gu has nothing to do with x, so I can get it out. So I have gu. And inside this term, I can put this one out as well. Constant, I put a constant out. And here, inside, this thing will become exponential negative u minus x squared. That's y, divided by 2 sigma squared. And then I have what? du. And I have dfxnx. That's it. Nothing special, just change of variables. Okay, and now we're getting closer to characteristic function. All right, so this is an important thing I want to say about characteristic function. So basically, this is a fact, and it's very good to know. The characteristic function of Gaussian. So just for general fact, let me use another notation, not x, not xn, not y sigma, but let's use z. So for Gaussian random variable z, here, okay, here we just call its variance alpha squared. So as a general fact, the characteristic function of z at t is taken this form. Expectation of negative t squared alpha squared over 2. That's it. Very simple form. And that's the characteristic function. So in the notes, we give some detailed explanation about how this is proportional to the Fourier transform of Gaussian density and how this is related to the uncertainty principle in quantum mechanics, but we will not talk about that here. Let's just focus on this fact, okay? Given this form of the characteristic function, and we can actually make use of it and introduce the characteristic function into our integral here. Okay, we want to deal with this. So basically, how can we, how can we make this into something of the characteristic function? And here is what we will use as the trick. We will see the connection between this term and this term. All right, so basically, you see, this is the definition of the characteristic function. But if we go to the definition of the characteristic function, you see there's equivalence. I'm basically reversing the order. This is the definition, and this is the result. The definition of the characteristic function here is expectation, another revisit. Expectation of I, T, Z, right? That's the definition. And then we can write it out, and it's actually, again, 1 over root 2 pi sigma. That's because Z is Gaussian. And exponential ITZ, lowercase z, for the value of for the argument in the density, times exponential negative z squared over alpha squared, okay, dz. So these two things are equivalent. So basically, you see, an interesting fact now comes out. What we can do is that we can actually use this result. Essentially, what this means is that we can always write an exponential function of this form as an integral. And this is exactly what we will use. Okay, so seeing this, right? And then let's see how we can replace this part. So following the same idea, you see, so given this fact, we can write exponential negative u minus x squared over 2 sigma squared. Following the same format, you see, now my sigma is 1 over alpha, and u minus x is t. All right, so this can be written as what? This can be written as 1 over square root 2 pi sigma integration exponential I t is u minus x. U minus x and what? And we can write this, okay, this is the z here, right? So basically we can have the, let me see, how should I say it? Probably it's better for me to, there's some notation issue. Yeah, okay. Here's something, pay attention. I want to use the notation t as opposed to z because that's easier to go back here. So t and second term, exponential negative u minus x squared. And as I said, alpha is 1 over sigma here. So I would actually have, I think I missed one thing. Sorry, my bad, 2. 2 here and sigma here and dt. Yep. U minus x, my bad. No. Sorry, I think I made it wrong. Sorry. Cross this part out. I'll start from the beginning. 2 pi sigma. And so here, the analogy, let me write it out so that you'll be on the same page with me. So basically, u minus x is the t, and sigma is 1 minus alpha over there. And inside the integral, I will write T as Z. Okay, I'll do those 3 notation changes, and now it's become clearer. So then here I have exponential I u minus x t. Second term, exponential to the negative. So Z is t. T squared, alpha 1 over sigma. So sigma goes here, 2 dt. Okay, I'm basically doing notation changes in this way. And then you see, this is what I have, and this is what I want. And why do I want to this? Because then this is a way for me to introduce the form. You know, I need an imaginary unit to be able to use the characteristic function. So I will put this part into here. And then characteristic function became part of my expectation of G at xn plus y sigma. That's the whole trick I want to use. So then you see, continue. Expectation G xn plus y sigma now can be written as what? I will put this into it. So basically, I think one thing that let me see if I'm missing it or not. So basically, I want to put this part into here. So I'll continue writing and see. So here, 2 pi sigma, okay, GU, these are all old things. And here, I'm going to put this part into it. So basically, I would have, this is about U, and this is about X. And I also have T, exactly. So I actually have 3 integrals for now, okay? So this is the integration for, these 2 are for du, dfx, and x. I have another for dt. So I'm going to do, okay, and I u minus xt. And
so this can be sigma over square root of 2 pi.
Sorry? So you're saying this part, right?
Yes.
Exactly. Sorry. Exactly. Yeah. My bad. This is because of this. I missed this part. Yeah, because of this. Thank you for catching it. Yeah. Okay, I made this correction because sigma is 1 over alpha. Okay, here we put this part in, and then dt, and then du, and then df x and t. That's it. Okay, now you see what I want for my characteristic function. Okay, so everything here becomes very good because I have, I have the imaginary unit introduced. And ultimately what I want, right? I want to have something appear here. This is what I want. This is what I have in the Levy's continuity theorem. And this is something by definition, ITXN. Okay, that's what I want. And if I write it out, it's what? It's actually exponential ITX dfxnx. Okay, you see, this is what I need. And how do I connect this to here? I almost have it, right? So I have IXT here, and I have dfxnt here. So I just need to separate the terms. So with this, you see, I continue. So I basically go down here. So for this part, I want to create this term out. So therefore, you see. So here, one thing I can cancel out is sigma, sigma cancel out, root 2 pi get combined. So I have 1 over 2 pi outside. And for the triple integration, now I'm going to get rid of 1 by removing this d, f, and x. So I have gu, and I have exponential I. Let me see, I'll make sure yeah, IUT. So this is also about U only. And I have about U and T, and I have exponential negative T squared sigma squared over 2. Okay. And I have what? I have exponential negative I x t. And then I have d f x n t. Sorry, not t x. My bad. I think this is a wrong thing. F x and x and d dt and du. Okay. So that's it. Here I need to put things here. I need triple integration. But one thing can already be getting out. That is this part. You see, this part is essentially what I have in the definition of hello, sorry, I was suddenly disconnected. Can you hear me now? Okay, great. Yeah, sorry, this is just like, the issue with remote education. As the chat box, video just cut out. Yeah, I believe. All right, so Zach, you can hear me now, right? Okay, great, let's continue. Okay, let's come back to this window. Okay, so we're still here. So what I was saying is that we have to, now we can get rid of x. So by taking out this integration. So that will give us 2 pi. So u, du, and dt will stay here. So we will still have gu and eiut e negative t squared sigma squared over 2. That's gone. But for the middle part here, I can do exponential I, I'm just going to write this way, I x negative t d f x n x. I put this as an inner integral, and then dt, and then du. Okay, finally, this is the characteristic function evaluated at negative t by the definition. So I have gu exponential iut exponential negative t squared sigma squared 2 characteristic function xn at negative t dt du. Okay, so I finally was able to express this term in terms of our characteristic function. So you see, where xn is, it's only in the characteristic function. Instead of the characteristic function, all the other terms has nothing to do with xn at all. You see, the u is not, right? And the t is not. So they have nothing to do with the characteristic function. They were only here because of the g and also because of y sigma is a Gaussian random variable. So now you see y sigma is not apparent anymore because we embed it with the u. That's it. Okay, so you see similarly, for the second term, I need to have expectation of gx plus y sigma. I replace xn by x. But you see, I only need to change the characteristic function. That is, I would have expectation gx plus y sigma as the same thing. I just copy the top IUT. Okay, here's the only change. It becomes the characteristic function of x at negative d, dt, du. All right, so you see, we're nice. We basically have this, okay? And what else? You see, we have this, and these two things are the only thing that differ between the two terms. And the Levy continuity theorem tells us that this converges to this for every t. Then can we say this converges to this? That's what's left. Given this converges to this, can we say the integral converges to the integral? That's the final question mark. And here we can use something we briefly mentioned but didn't prove in our previous lectures. That is the dominated convergence theorem. That's the only thing we will need. Okay, and why is that? Why does that apply here? The thing is that the dominated convergence theorem is about what? What we told you is that it tells you under what condition can we go from almost sure convergence to convergence in expectation, right? That's what we tell you. And almost sure convergence is, as a review, almost sure convergence is that for the realization of your random variable sequence and the random variable limit. For every realization, you have that fixed sequence converge to that fixed limit, and it holds for all realization with probability 1. That's the almost sure convergence. And here, it's exact. It's actually the same case, you see. The connection is that for any given t, we do have the thing inside the integral. Here, this converge to this. And also, I will say for any given u and given t, we have gu this times this times this times this. The function converge to this function for any given u and given t. That's just like the one realization of our almost sure convergence. But what we're interested in is the integral, double integral of this function over u and over t. And does the integral still converge to the integral? That's like expectation convergence. So that's why you see we are having the same flavor here. A realization is a function given a particular value. An expectation is the integral of that function over all possible values. So I hope this can make you see the connection between, point-wise convergence in a function and integral of a function convergence versus the almost sure convergence and expectation convergence. So you see the connection between function and random variables. Does that make sense? Maybe I can write it down. Hopefully that's clear. So instead of just saying. So you see, here we want, so we have what? This function g of given any u and t. okay, we have GUIUT negative t squared sigma squared over 2 ix, sorry, my bad, phi xn t, phi xn negative t, phi xn negative t. This thing, this on the left-hand side, converge to GUIUT if negative t squared phi x negative t. So we have that. For any given u and t, I have the pointwise convergence, right? So in function, we call this pointwise convergence. And now the question is, can we have integration convergence? So integral. So basically, we want this du dt converge to this du dt. That's the question. And can we go from here to here? And here, what I was saying is that DCT allows us to do it, the dominated convergence theorem. So for dominated convergence theorem, we just need to show that, okay, the function, the pointwisely convergent function has a bound, has a finite bound. So basically, DCT says, we just need to have an upper bound on this thing. GUIUT does this have an upper bound? Yes. And here we're going to use the boundedness of G again. We know G is bounded by capital B. And what else? This is actually bounded as well. This is bounded because it's by the Euler's formula, right? Cosine sine thing. This is bounded by 1. And this thing is also bounded. We know this because by its special form, this exponential function, it's bounded below 1. And the characteristic function, we already said it's bounded. And also you can see this is bounded because this is Gaussian's characteristic function. We already gave you that connection. So this is bounded by 1, 1, 1. So basically I will say this is bounded by B. This is bounded by 1. This is bounded by 1. And this is bounded by 1. So every term is bounded. So that's why the whole function is bounded. And we have, so it's actually having a unit upper bound of B. So we're done. So basically, you see the dominant convergence theorem applies so that for the pointwise convergence, if the function has an upper bound and the upper bound doesn't depend on its value at all, then we can apply the dominant convergence theorem to say, okay, its integration also converges. That's what we only need here. And I was trying to make a connection with almost sure convergence and expectation convergence. So basically, you can see here pointwise convergence is having some connection with almost sure convergence. And the integral convergence is having some connection with the expectation convergence. So I'll just write this. Why is that? Because you see, what the function does is that you give it a value, it outputs a value. And that's just equivalent to having a realization here. So every value you input into a function give you a sequence of function values and the limit value. Here, for every realization, you have a sequence of numbers and the limit. So you have some connection there. And here, the integration is that you integrate over possible values of the function, of the domain of the function, and what's the output? You take the integration. Here, expectation is also, so given all the possible realization and their density, you take expectation. So expectation is essentially an integration. And this almost sure convergence is about particular realizations. And if you have that, it's like for every possible value in the domain, you have the convergence, pointwise convergence. That's it. Okay, so I would say this is the more general form of the DCT, and this result is actually an application of DCT to the random variable sequence. Any questions, Zach? I think you wanted to say something.
Yeah, I was curious. So you're associating.
Sorry, I couldn't hear you clearly.
Can you hear me now? Sorry.
Yeah.
So you're associating pointwise convergence with almost sure convergence, but of course, pointwise convergence of the CDF is just convergence in law, not almost sure convergence. So when you say pointwise convergence, you mean like pointwise convergence of an arbitrary function of the CDF?
An arbitrary function. None, yeah, definitely an arbitrary. I'm just so here. So basically here, this is more about so this left-hand side has nothing to do with probability, has nothing to do with statistics. It's just a mathematical statement. I'm saying the analogy. I'm saying why the DCT can be used to prove this. I was saying that the DCT in this form is a special case, and this is the general DCT.
Okay.
Yeah, I'm saying that, so basically, fundamentally, I want to say that a random variable, what is that? A random variable is actually, it's actually a map. It itself is a function. It maps from your sample space to what? You can think, okay, maybe let me put it this way. You can think about the random function as a map from uniform, understand uniform. So you can see a function, a random variable itself is a function, right? It maps from some space to other space. And basically you can consider the random variable value as the function value here. So it's like, maybe I should put it this way. So for a random variable, it means for every value you give it, it gives you another value. So by changing the random variable as a function, you can obtain different distributions of the random variable. So you can get a Gaussian, you can get a uniform, you can get exponential. You just need to change the map. How you map from a space to another space. That's a random variable. So an analogy here is that for the almost sure convergence, it means that for any input I give the random variable value will converge to this random variable value. So that's similar to the function's pointwise convergence. Does that make sense?
Yeah, I think I'll have to think about it later, but yeah.
Okay, yeah. Yeah, but just don't think about CDF or anything. It has nothing to do with the form, the special form. Yeah, but I will put it this way. So if this is a little bit too abstract for now, that's totally okay. But yeah, but I just want to put our emphasis back to the Levy's continuity theorem. That's the emphasis. So we just finished proving, this is probably the longest proof we have given so far. So we just proved how we can go from the right-hand side to the left-hand side. Still, we use the Hessian statement 2, statement B. But I think the key trick here is that in order to make use of the characteristic function, we introduce a perturbation Gaussian. And that's a very, very useful trick. And you can see why Gaussian distribution, Gaussian variable is so widely used, because it has super nice properties, including this fact I said. So this fact is a very nice property of Gaussian That is, its characteristic function has this clean closed form. That's its characteristic function. And magically, this form is very, very similar to the Gaussian density form. It's basically the same term, the same exponential term in the density, but we just take an inverse of the variance. In the density, the variance is in the denominator, but in the characteristic function, the variance becomes in the numerator. So that's a very magical thing. And because of that, we can prove the Hessian B. That's it. So continuity theorem is the ultimate, you can almost treat it as important as the definition of convergence in law. So you can prove the convergence in law, convergence distribution in two ways. One, as Zach already said, is to prove by the definition, you do have the convergence of CDF, point-wise convergence of CDF for every value, or you can prove the point-wise convergence of the characteristic function for any value. So here's the summary. Here's a summary. So basically, we would have this. The convergence in law can be proved in two ways. One is the CDF convergence. And I would say any X in continuity set. Don't forget about this. In the continuity set. And the second is about the characteristic function convergence. That's the Levy's continuity theorem. That's it. Okay, so that's about the convergence in law, some foundations. And then also I want to give you some little preview that the Levy's continuity theorem is why we can prove, is one way to prove central limit theorem. So with that, the central limit theorem proof becomes much more straightforward. Okay, so another thing I want to say a little bit about is in the notes. Although I said I'll try to make things simpler, so we just use the scalar, not vector. But still, this is something good to know, especially I think especially it's very, very useful for your own paper writing in the future. That is about the derivative of vector value functions of a vector variable. Okay, so just some notation clarification. So basically, it's something you will see in the notes, even if we may simplify in the lectures. So it's about how we write the derivative of a value, of a function whose argument is a vector, but whose value is a scalar. So here, let's first go talk about this. So the function takes a d-dimensional vector as input and outputs a scalar. And we call its derivative as gradient, right? You may have heard of this name a lot in machine learning nowadays. So gradient is actually the first order derivative of such f. So in the notes, we use this notation f dot, but please note that you may see that triangle thing, right? So this, you can also see this a lot. This is another notation that's frequently used. So here, I just want to make sure that here in our definition in the notes here, the gradient is defined as a row vector instead of a column vector. And this is something every textbook need to make sure they define it in the beginning, because some books use it as a column vector by default, some as a row vector. If you didn't think about this clearly, you may get the derivation, the notations confusing. So here it's defined as a row vector. And we write it just as partial f partial x1, the first dimension, to the partial derivative of the dth dimension. That's it. So we write it as a row vector. That's just notation used in the notes, and I follow that book, the large sample theory book I recommended by Tom Ferguson. And also in this book, if we have another function, so basically G, okay, that takes a vector input and outputs a vector. So this is what we call a vector valued function. So its value is not a scalar, but a vector. This is actually very common in physics. We have those vector value functions, but maybe not so common in statistics. But still, it's useful because it's useful for us to get a second derivative of f. So for G, here we basically define its derivative here as a matrix. Okay, so this is how we define G. So because you know G itself, right? So here G, we can write itself as a vector, so G1 to Gk. So it's like a vector of functions. Every function G something maps from Rd to R, right? Every G something is a scalar value function, but together they form a vector value function. So the definition of the first order derivative of G is this, it's G1 dot to Gk dot x. That's it. And now you see the convenience of defining the first order derivative, the gradient, as a row vector, because you see this G dot is then a K by D matrix. Every row is just a row vector. It's just the gradient of this component, right? So we will basically have the matrix as this. So it's partial G1, partial X1 to partial G1, partial XD. And here's partial GK, partial X1 to partial GK, partial XD. That's it. That's how we define the gradient of a vector value function. So you see, given this gradient itself is already a vector value function, then if we want to take the second order derivative of f again, it becomes a matrix, right? And what's the dimension of its matrix? Given this is a d-dimensional function, it maps from Rd. So f dot itself maps from Rd to Rd. So its gradient is, its derivative is a d by d function. And that's what we call the Hessian matrix. So the second order derivative of f. So here I'm going to continue. So that is, so the f dot dot itself maps from Rd to Rd by d. It's a matrix. So you see here, I need to write f dot maps from Rd to Rd. It's a vector value. And f dot dot is mapping Rd to Rd by d. So, and that's what we call the Hessian matrix. Yeah. So I'm not going to write it down because it's very straightforward. You just take the derivative, partial derivative for every dimension again. Okay, so that's it. And for those vector value functions, so we still have so basically we still have those chain rule, the product rule, and the mean value theorem as in the univariate calculus. So everything still follows along. So one thing I just want to say a little bit about is about the product rule. So I think that's quite useful. So basically, I think one thing that's quite useful, product rule, is that if you have F that maps from D-dimensional to K-dimensional, and you have G that maps from D-dimensional to K-dimensional as well. So if you have these two functions, then their output are in the same dimensions, right? So if I define Hx to be Fx transpose Gx. So now you see H is a scalar. So H maps from D-dimensional to one dimension. And then what is the derivative of H? So this is something we can actually have quite easily. You see, the derivative of Hx by our definition is a D-dimensional row vector, right? This is a gradient. So then you see what we will have. So it's actually equal to G. Okay, so here by our definition, we can actually write it as Fx transpose G dot X. Okay, so by the dimension, it's consistent. So this is 1 by K, and this is K by D. Because this is 1 by D. Okay, and the second term is Gx transpose F dot X. Similarly. So why I want to say this is because the definition of a gradient being a row vector or a column vector will decide how you write the right-hand side. So you need to always make sure the dimensions are matched. Otherwise, there will be some issues in your derivation. That's the thing I want to mention. Yeah, but just in the notes in this class, we use row vector, and that's something I also prefer. I think that makes things easier. Okay, so a last little thing before we finish today is the consistency. So consistency is something not about convergence and law, but it's something good to talk about. So you can think about the convergence and law we introduced, the Hillenbrand and the Levy's continuity theorem as applications of what we said before. Those different modes of convergence, right? It's like a very important application. Another application is the consistency. So in consistency, we have two ways of saying that an estimator is consistent. One is strong, one is weak. So for the weak consistency, we just use the convergence improbability. Sorry, that's what we said with convergence. And for the strong convergence, with strong consistency, we say it's almost sure. Okay, so here in statistics, we have things simpler. So this is an estimator of sample with size n. And this is considered as random. And this theta is parameter. And in the frequentist paradigm, this is actually quite a frequentist thing. But later, people may have, Bayesian people may try to make some connections, but classically it's a frequentist thing, and it's considered as fixed. So you see, it's much easier than our general discussion because now your limit is fixed. We only have randomness on the left-hand side, right? And so an estimator is random because the sample is random. When you draw another sample of size n, you get a different sample. That's a different realization of your sample. As a result, your estimator has a different realization. And here we are just saying weak consistency means that, okay, your estimator overall in probability is getting closer and closer to the constant. And strong means that in every realization of your draw, you draw the sample one by one by the sample size. In every realization, the sequence of the estimator values converges to theta. So I think this is a way for you to see what's the difference between strong and weak. And also in the weak convergence, as we said before, for convergence and probability, you may not have convergence in every realization, but overall, it's getting closer and closer to theta. So yeah, I hope this makes sense to you. And we'll stop here for today, and we will give some more discussion on Thursday. So for today's seminar, I want to make an announcement because I think this is something that's worth attending, just as probably not very different from the last one. So I'll stop sharing first. So today's, and let me see, I'll quit. Okay, I'll stop recording actually. So in today's seminar, I have invited